title of my work is Fault Detection and Diagnosis for Central Heating Systems using equipment emulators and vibration monitoring techniques. So this work began by asking ourselves this question: how can we improve the performance of Canada's legacy building stock? And so we observed that much of my experience lies in these three fields. We look at building science, mechanical engineering, and data science. And at the intersection of these three topics, we found the topic of HVAC fault detection and diagnosis. So when we look at a building, we know that there are many systems that exist in there. And with my experience, we found that HVAC systems is something that we can use to leverage or improve the performance of buildings in Canada. And the field of fault detection and diagnosis essentially is some sort of routine that observes the operation of equipment, and it evaluates whether or not faults, something that is improperly working, exists in these equipment. The research objective that came out of this overlap includes this. So this research focuses on the development of an FDD methodology to permit buildings with building automation systems to diagnose hydronic heating system faults. And when we speak about hydronic heating systems, we're focusing on what I've highlighted in the figure of the boiler and the pump specifically. And that is one subsystem of the many subsystems that exist in HVAC systems. And so that's the focus of this work. Now, the research questions that came out of this include the following. Firstly, we asked what data points observed by the BAS should be included to create FDD for non-condensing boilers. We asked what level of accuracy can be achieved with those observed BAS points. Third, we asked which features need to be included to create FDD for water pumps using vibration monitors. And finally, what level of accuracy can be achieved with those features. So overall, this work contributes to several things within this domain. Firstly, we are presenting a novel method for improving the performance of legacy buildings. So we present two methodologies of a non-condensing boiler and of a pump using two unique methods. This research confirms or adds new knowledge to the field of HVAC FDD through these two methodologies. Furthermore, we provide increased insight for building owners and operators about equipment operation and performance. So using these sensors that are installed in these equipment already, they get a better understanding of how it's operating within the equipment. Next, we expand on the topic of physics-based fault modeling for boilers, and I'll go more into detail about what that is. And finally, we're providing energy costs and equipment saving potential for these buildings. So the methodology was split up into two themes. So you may have noticed that we talk about the boiler and the pump. And so these are presented as two methodologies. And generally how it's going to work is that we're going to start with some sort of sensor output, such as the one depicted here. And what we could do is perform this methodology in order to provide a final result. And what we have here is a machine learning classification output. And this is essentially the core of our fault detection, is this final result. And so I'll just go into a little bit more detail of what that means. So for the boiler model, we began with the boiler model development. And so the software of SimScape was used, and SimScape is it's a software that models physical systems. And so a physical system includes physical things such as a boiler. And a boiler consists of essentially a combustion chamber, such as the one depicted here, and the heat exchanger. And so this image is actually the emulator that we've developed, which emulates boiler performance. The next step after developing the model was model calibration and validation. And so calibration and validation was achieved by comparing the outputs to standards and manufacturer specifications. And here we have listed several of the outputs, or rather all of the outputs that we would compare with the manufacturer and with our boiler emulator. Once the model was calibrated and validated, we were able to perform dataset generation. So what we observed, what I did was I created 14 unique boiler models across various manufacturers of different sizes and inputs, and each of these boilers simulated 3 types of faults across 4 different operating ranges. And so for each boiler, we generated roughly 10,000 data points of steady state performance for each boiler model. So we had roughly 14,000 data points at the end of this. And at the end of that, we took the data set, we tailored it, and we applied machine learning algorithms in order to perform classification. And that machine learning algorithm was the core of our fault detection. For the pump FDD, we began with vibration signal pre-processing. So as you can see in this first image, this is a full-length vibration signal. It's only 3 seconds long, but it's sampled nearly 80,000 times in those 3 seconds. And it's quite limited in its information. So what we can actually do is split it into smaller samples. And what we did is we took these original full-length vibration signals, which were 20 vibration signals, and we produced almost 2,000 samples across 3 bearing faults. So with these samples, I was able to perform feature extraction, which takes the statistical properties of each sample and collects the important information regarding each of these samples. And the next step was feature reduction. So data science methods were used to reduce those 18 dimensions or those 18 statistical features to a lower dimension, something that's manageable, such as 3 dimensions. And finally, we've created a data set that could be applied with into machine learning algorithms that perform the fault detection and diagnosis. And so that is an overview of the methodologies that we've used for this, this research. And so I can begin with the research results. So presented here is, first of all, a very rudimentary boiler model. And in the second image is the boiler model that I actually emulated, the Weizmann-Viteron series. And this is a non-condensing boiler. And so essentially, the boiler works through these 2 main components. We have a combustion chamber where the fuel and the air combine and are combusted, and that produces the heat energy required to warm up the water. And those hot gases then pass through a combustion gas water heat exchanger. And there is the heat exchange that heats up our water. And what is output is the supply water. That's the hot water, and what's outputted to the environment is the flue or the exhaust gas. And so in this system, we observe 3 faults. Now, the first fault is excess air, and that's most likely, or it is rather, in the combustion chamber, which is the circular part of the model, or what is listed in the simplified picture. And so combustion air would indicate that there's an excess amount of oxygen, nitrogen, any kind of just components of air that reduce the efficiency of combustion and reduce the temperature of the flame. The next type of fault is water scaling. So with this type of boiler, it's sectional. So each square is a separate section, and the water goes through those sections. And so any kind of calcium deposits would start to occur inside of the sections of the boiler where the water passes. And the last type of fault is air fouling. And so any kind of soot that might come from the combustion gases would start to accumulate on any of these passes of the heat exchanger, and they would start to reduce our performance of our equipment as well. So what is presented is essentially a boiler model that uses easily measured system outputs to identify which fault is causing changes in performance, but as well, this methodology shows the level of degradation of these faults, and you'll get to see what that is in further detail. So the next step was model calibration and validation. There was 11 total boilers of different sizes, and generally we see good agreement with the validation results, the calibration results as well. There's a slight underestimation, but it's consistent throughout. And so we've found that this generally shows that the model is in agreement with what is expected with the published manufacturer data and the standards. And so with that, I generated a data set of observable outputs of this emulator. And these include the following 8. We have the flow rates of the fuel and the water, the temperatures of the outdoor air, the return water, supply water, the temperature of the combustion gas, the exhaust gas, and the thermal output. However, many of these outputs aren't necessarily observable by common sensors, especially sensors that are in older legacy buildings. And so this addresses our first question: which data points can we use for non-condensing boilers that are easily observed by the BAS system? The bolded data points or outputs are the observable BAS points that are easy to measure, and they are commonly measured, and they include the water flow rate, and the temperature of outdoor air, the temperature of the water coming in and out, and the temperature of the exhaust gas, the gas leaving the system. And so with that, we have a data set of observable BAS points across multiple faults, across multiple operating conditions, and we can answer that second question of what level of accuracy can we achieve with this output. And so here's the summary of our first iteration of data sets. And what we can see is various manufacturers for the boilers across four classification schemes, our machine learning algorithms. And bolded is our best situation, where we have roughly 90% accuracy. And the results are generally good. They provide a decent amount of accuracy. And so what we can do is actually visualize these results in individual charts. And that's what this looks like here. This is a confusion matrix. And so this is an output of our machine learning algorithms. And what we have on the left axis is our actual fault. So that's what we've emulated, that's 100% true what it should be. And on the x-axis, we have the predicted fault. So that's what the machine learning algorithm was taught to think, was taught to believe the certain fault would be. And so at the intersection of these two labels, for example, first one here, that would indicate, a perfect classification, or you would want the intersection of these to be darker hue, meaning it's a higher level of accuracy. That means our machine learning algorithm can distinguish the data properly, accurately. But what we notice right off the bat is the following. In the squared box, we have a lot of misclassification, and a lot of the adjacent classes are experiencing some sort of confounding. And what we find is that the excess error doesn't change in performance sufficiently between intervals for it to be accurately classified. And something was needed to be done because this was our source of most error. And so, well, the second iteration of this data set considered excess error as a single class. And the logic for that was that excess error isn't necessarily a gradual performance degradation. Rather, it's a damper that is working or not working. And so the data set can be classified as excess error exists or doesn't exist. And so we get the second iteration of the data set. And generally, we see a significant increase in accuracy with random forest and support vector machines, the bottom two, achieving nearly double-digit increase in accuracy. And so these results can be visualized in the same manner with the confusion matrix. And we have the following results. Right away, you can see the excess error, relabeled as one class, is perfect, essentially, in its classification ability. And the change in accuracy is, upwards of 14%. And so we've shown that this type of methodology for a boiler FDD is accurate. This style of data set is sufficiently accurate for it to be able to predict faults, but not only predict faults, but predict the faults at certain levels, as the fault becomes more and more dominant in the system. And so that concludes the boiler side of this. So we can jump into the pump now. This is a picture of a pump that we got to work with, and they tasked me with identifying a method for performing fault detection on their manufactured pumps. Unfortunately, they didn't have a data set, so I had to use an experimental data set of a roller bearing, and that's pictured here. And most rotating machinery, including pumps, use roller bearings in their equipment. And so this data set observed two of these components. We have the outer race of the bearing, and we have the inner race of the bearing. And we can actually measure the vibration of this pump, this bearing, and we can observe the changes in the vibration signals as faults become present. And so in the first case, image A, it looks noisy, doesn't look like much, which is good. That means there's no significant and there's nothing significant happening within the equipment to have any distinct look. But if we look at the second image, it's inner race failure, or this image B, you can see that there are several small peaks and a significant impact. And the same with the third image, where we have more observable impacts caused by this outer race failure. And so the goal is to essentially distinguish these three types of signatures and perform the fault detection by distinguishing these three. And so what happens was we had nearly 2,000 samples of our vibration across three types of faults. We apply statistical equations to them in order to gather essentially the essence of them. And what outputs is a data set of 1,960 variables by 18 statistical features. And so what we can do is start comparing these features against each other in order to understand how well the features capture the difference between data. And so we have here two types of images. We have the time domain and the frequency domain, and two examples of the features that are in the data set. And we can't clearly see any distinction between these types of labels besides the green and the orange. And so we can actually perform a new type of a more novel signal processing technique called enveloping. And it's a three-step process that essentially takes this signal and amplifies the frequencies associated with the fault. And this final image here depicts that it proves that there exists this frequency in the samples that we have. And if we apply the feature generation onto this resulting enveloped signal, we actually get the best results from that data. And so this is an example of those enveloped features where the data is very clearly separated from each other. So normal is completely separated from outer race, unlike what the previous set of features had. And so what we can do is apply machine learning to this. And we can actually, I'll skip this. We can apply machine learning to this smaller data set of just enveloped features. And we can see that the accuracy is very high. We average 99% accuracy for our pump diagnostics. And so what we've proven is that this methodology can certainly give you very high accuracy using this novel signal processing of enveloping. And so that concludes the work for the boiler and pump, and I'll just go over some of the conclusions from that work. So first of all, we've created a computational model of a non-condensing boiler that can accurately simulate performance according to manufacturer specifications and the standards. Next, the model was able to emulate three common faults found in boilers. Next, these faults were identified using easily measurable sensor data points of a building automation system. And finally, we've shown that the machine learning algorithms were able to predict faults with a high degree of accuracy, averaging roughly 94%. For the pump, experimental data was used for pump fault detection and the experimental data was of bearing failure. And using a combination of signal processing techniques, statistical feature generation, and various data science methods, I was able to get a very high accuracy of roughly 99% using these methods. And overall, this thesis shows that fault detection and diagnosis algorithms can be created both using simulated and measured equipment data, and both of these achieve a high level of accuracy. And in general, these FDD results can be used for continuous commissioning, predictive maintenance, and to further increase the efficiency of common HVAC equipment. And so that concludes my research. Thank you, everyone.